In this video, we'll talk about first-order linear equations and how we can go about trying to solve them. We mentioned that linear equations will be easier to solve than nonlinear ones, but the only type we've solved so far has been nonlinear. So what can we do with linear equations? Well, what do linear equations look like in general? Well, we know we have to have our y prime and our y sort of separate from each other, not raised any powers, not multiplied each other, not inside any of their functions, just sort of separate by themselves. Which means sort of the most general first order linear equation looks something like a function a of t times y prime, a function b of t times y, equaling some function c of t on the other side. Right? If I can't multiply the y primes by each other, or the y's, I can't raise them to their powers, they can't be inside of their functions, this is the most general thing you can have. Some arbitrary functions, a of t, b of t, and c of t, set up in this sort of way to produce this differential equation. Now, when we're trying to solve these things, we want to put them in some sort of standardized form, and that's going to be making sure the coefficient of y prime is just 1. So the standard form for an equation of this form is y prime plus some function p of t times y equals some function g of t. Now, if we're talking about a first order linear equation, we are talking about something that looks like this. You've got your y prime, you've got your function p of t that's attached to the y term, and then g of t is on the other side of the equation. That's the best we can do because there can't be other y's in any weird forms on this equation. Now, some definitions for these. If we have this first order linear differential equation, we say that this equation is constant coefficient if this function p of t is a constant and doesn't change depending on t. That is, if the coefficient of y in this equation is a constant. Otherwise, it's non-constant coefficient. We say that this function is homogeneous, or homogeneous depending on who you talk to, if this function g of t, this right-hand side function, is 0, and it is non-homogeneous otherwise, or non-homogeneous. And we'll see these equations have slightly different properties, but we just want these words to talk about them as we go forward. Now, if the equation is homogeneous, if the right-hand side is 0, then it's separable. I move the p of t y to the other side, divide by the y, get 1 over y dy dt equals negative p of t, and then we can solve it separable. If not, what else can we do? Well, an example to illustrate what we can do is something like this. T squared ty dt plus 2ty equals e to the t. Right, this is not separable. I can't sort of isolate things in any nice way. But this left-hand side here is very particular. What is this left-hand side? Well, I have two terms, one of which has dy dt, one has y in it. What else do we know does that? Well, the product rule does that. Right, if I have a function f of t times g of t, I differentiate this, I'm going to get f prime of t times g of t plus f of t times g prime of t. One of these has a dy dt, a derivative in it. The other has the function itself. So can I write this left-hand side as a product rule? In this case, the answer here is yes, because if I look at the function t squared times y of t and differentiate that, I'm going to get t squared times dy dt plus the root of t squared, which is 2t, times y. That means I can rewrite this entire differential equation as the derivative of t squared y of t equals e to the t. And now that I have a derivative on the left and a function of only t on the right, I can now integrate both sides in t, and by the fundamental theorem of calculus, the left-hand side becomes t squared times y of t, and the right-hand side becomes now e to the t, the nth derivative of e to the t, plus c. Then I can just divide through by t squared to solve out for y to get my answer as y of t is e to the t over t squared plus c over t squared. Notice here the form in which I have c divided by some other function. That's going to be a common theme throughout this section. Now, the key point here was I was able to recognize the left-hand side of the equation was a product rule, and then with that, write it as a product rule derivative. It is now a derivative. I can then integrate both sides to solve for the answer. A lot of times that won't be the case, and we'll discuss ways in which we can take an equation like this and make it be in this form where the left side is a product rule derivative. And that's why linear equations are so much better, because we can always, no matter what the setup is, we can always make the left-hand side into a product rule derivative. And that means we can always solve the equation, always have a specific way we're going to go about solving these linear equations, whereas for other types, that's not necessarily the case. But for these, we have a specific way, method, and formula for how we're going to solve out these equations. That gives you the idea of what these look like and how we're going to go about solving them in the future.